Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hey everyone. I am PS Chatterjee with you, and I'm fired up to be back with your channel, Structural Design Only, a channel with different vision. Welcome back to the Power of Shapes. This is part 3 of the series, where we delve deeper into the fascinating world of structural engineering. Today, we're tackling the concept of moment of inertia for 3 fundamental shapes: circular, trapezoidal, and compound trapezoidal sections. We'll be breaking down complex formulas into easily understandable steps, using a combination of PowerPoint presentations and practical Excel calculations. Whether you're a seasoned engineer or a curious student, this video aims to illuminate the intricacies of moment of inertia. Get ready to unlock the power of shapes and their impact on structural design. Let's dive in. Oh, and a quick announcement before we start. Today, August 11th, 2024, Structural Design Only is celebrating its 4th birthday. We couldn't have reached this milestone without your incredible support. Stay tuned for special content and giveaways as we commemorate this special occasion. Now, let's begin our journey with the classic circle. This simple shape holds the key to many structural calculations. Let's see how we can determine its moment of inertia. Let's introduce a crucial concept before diving into the calculations for a circular section: the theorem of perpendicular axes. This theorem is fundamental to understanding moment of inertia. As you can see on the slide, it states that if we have a plane section and 2 perpendicular axes, xx and zz, intersecting at point O, the moment of inertia about an axis yy perpendicular to this plane and passing through point O can be determined by simply adding the moments of inertia about the xx and zz axes. In mathematical terms, Iyy equals to Ixx plus Izz. This theorem will be invaluable when we calculate the moment of inertia of our circular section. Now the question is how we can prove the theorem of perpendicular axes. To do that, we have to consider a circular plane on xz plane and y-axis of this plane is perpendicular to the circular plane and all this axes are passing through O. Now consider a lamina P on this plane and distance of this lamina from O is OP, and OP equals to R and area of this lamina equals to dA. Perpendicular distance of P, from x and z axes are small x and small z respectively. From geometry we can say, R square equals to z square plus x square. Say moment of inertia of this lamina, P, about xx, zz and yy axes, are Ixx, Izz and Iyy respectively. Now we know, Ixx equals to dA into z square. Izz equals to dA into x square. And Iyy equals dA into r square. And r square equals to z square plus x square. Therefore, we can write, Iyy equals to dA into r square equals to dA into z square plus x square equals to dA into z square plus dA into x square. We already know that dA into z square equals to Ixx, and dA into x square equals to Izz. Finally we proved that Iyy equals to Ixx plus Izz. Now that we've grasped the theorem of perpendicular axes, we're ready to tackle the moment of inertia for a circular section. In the next slide, we'll delve into the step-by-step process of deriving the formula for this fundamental shape. Let's delve into calculating the moment of inertia for a circular section. Imagine a circular area with a diameter d and radius r. Now, consider a tiny ring within the circle, located at a distance x from the center and having a thickness of dx. The area of this infinitesimally small ring, which we'll denote as dA, can be calculated as the circumference of the ring multiplied by its thickness. Therefore, dA equals 2 into pi into x into dx. To find the moment of inertia of this small ring about the y-axis, we multiply its area by the square of its distance from the axis. This gives us Iyy sec equals 2 into pi into x into dx into x square, which simplifies to 2 into pi into x cube into dx. To determine the moment of inertia for the entire circular section, we need to integrate this expression from the center of the circle, x equals 0, to its outer radius, x equals r. Performing this integration yields. Finally, the moment of inertia about the y-axis, denoted as Igyy, is equal to pi by 2 multiplied by d by 2, to the power 4, which simplifies to pi into d to the power 4 divided by 32. Remember, from the theorem of perpendicular axes, Igxx plus Igzz equals to Igyy. And in this case, Igxx equals to Igzz. Therefore, Igxx and Igzz are equal to half of Igyy, which is equals to pi into d to the power 4 divided by 32. Divided by 2. Simplifying further, we arrive at the final expression for the moment of inertia of a circular section about the xx or zz axis, Igxx or Igzz equals to pi into d to the power 4 divided by 64. In our next slide, we'll shift our focus to calculating the moment of inertia for a symmetrical trapezoidal section. Let's now derive the moment of inertia for a symmetrical trapezoidal section about its base. Consider a symmetrical trapezoid ABCD with bottom base AB, equal to A, top base CD, equal to B, and height, AC, H. Imagine a thin strip within this trapezoid, with thickness, dx at a distance, x, from the base AB. Let's denote the length of this strip as k. Due to the trapezoidal shape, the length of the strip changes as we move up the height. This change in length can be expressed as A minus B by H. Therefore, the length k can be calculated as A minus, within bracket, A minus B multiplied by x, and divided by h, which simplifies to AH minus AX plus BX divided by h. The area of this strip, dA, is equal to the length k multiplied by the thickness dx. Substituting the value of k, we get dA equals to A into dx minus A into x into dx by h plus b into x into dx by h. To find the moment of inertia of this strip about the base, we multiply its area, dA, by the square of its distance, x, from the base. This gives us dA multiplied by x square, which simplifies to a into x square into dx, minus a minus b by h into x cube into dx. To obtain the total moment of inertia about the base, denoted as IAB, we need to integrate this expression with respect to x from 0 to h. Performing the integration, we get IAB equals to a by 3 multiplied by x cube, evaluated from 0 to h, minus a minus b by 4.h multiplied by x to the power 4 evaluated from 0 to h. Simplifying this expression further, we arrive at IAB equals to a into h cubed by 3 minus a minus b into h cubed by 4, which can be combined to give 4a 3a plus 3b by 12 multiplied by h cubed. Therefore, the final expression for the moment of inertia of the symmetrical trapezoidal section about its base, IAB, is equal to a plus 3b divided by 12, all multiplied by h cubed. This formula provides a fundamental tool for analyzing the structural behavior of trapezoidal sections. In the next slide, we'll shift our focus to determining the moment of inertia of this symmetrical trapezoid about its centroid XX and ZZ axes. This will provide us with a comprehensive understanding of the section's resistance to bending. Welcome back. In this slide, we will explore the theorem of parallel axes, which we briefly touched upon in our previous lesson, the power of shapes, part 2. This theorem is crucial for establishing the formula for the moment of inertia of a symmetrical trapezium about its XX axis. Let's delve into the theorem. If the moment of inertia of a plane about an axis through its center of gravity is denoted by IGXX, and an axis parallel to the base, the moment of inertia of the area about the base, IAB, at a distance r from the center of gravity is given by IGXX equals to IAB minus a into r square, where a equals to total area of the section. The diagram illustrates a symmetrical trapezium with relevant axes and dimensions labeled. In our next lesson, we will utilize this theorem to derive the formula for the moment of inertia of a symmetrical trapezium about its XX axis. Stay tuned. Title of this slide you are watching is Moment of Inertia of a Symmetrical Trapezium about XX axis. This trapezium is symmetrical about its z-axis. In this slide, we will calculate the moment of inertia of a symmetrical trapezium about its XX axis. We'll utilize the formulas we derived in the previous slide using the theorem of parallel axes. Let's begin. Say the area of the trapezium is A, therefore, A equals to A plus B into H by 2. Say the distance of CG from base is R. Therefore distance of the centroid from the base, R, equals to A plus 2B into H by 3 into A plus B. Moment of inertia about AB, IAB. We have already calculated this value in the slide number 5, as IAB equals to A plus 3B into H cubed by 12. Say moment of inertia about gxx equals to igxx. By using the theorem of parallel axes, we know that igxx equals to iab minus a into r square. By substituting the values, we get igxx equals to a plus 3b into h cubed by 12 minus a plus 2b whole square into h cubed by 18 into a plus b. Simplifying this equation leads to igxx equals within bracket a plus 3b into 3 into a plus b minus 2 into a plus 2b whole square bracket close into h to the power 3 by 36 into a plus b. Further simplifying, we obtain igxx equals to, within bracket, 3a square minus 2a square plus 9ab plus 3ab, 8ab plus 9b square minus 8b square, bracket close into h cubed, by 36 into a plus b. Since the section is symmetrical about the zz axis, igxx is equal to igzz. Finally, we have moment of inertia about x and z axes passing through the centroid. igxx equals to igzz equals to a square plus 4ab plus b square into h cubed by 36 into a plus b. In the upcoming slides, we will utilize these formulas to determine the moment of inertia of a compound trapezoidal section. Title of the slide you are watching is Steps for Moment of Inertia of Compound Section. In this slide, we will outline the steps involved in calculating the moment of inertia of a compound trapezoidal section, specifically the section ABCDEF. This section is composed of a rectangle, ABCD, and a trapezium, CDEF, making it a symmetrical compound trapezium. The z-axis passes through the middle of the bottom base AB and top base EF, which are parallel to each other. Let's go through the steps. Step 1. Denote the area of the trapezium as A1 and the area of the rectangle as A2. Step 2. Calculate the total area, A, by summing A1 and A2. Step 3. Determine the distance of the centroid of A1 from base AB, denoted as R1. Determine the distance of the centroid of A2 from base AB, denoted as R2. Step 4. Calculate the distance of the centroid of the total area, A, from base AB, denoted as R. This is given by the formula, R equals to A1 into R1 plus A2 into R2, by A. Step 5. Calculate the moment of inertia around the centroid of A1, denoted as IGX-A1. Calculate the moment of inertia around the centroid of A2, denoted as IGX-A2. Step 6. Calculate the moment of inertia of A1 around AB, denoted as IAB1, using the formula, IAB1 equals to IGX-A1 minus A1 into R1 square. Calculate the moment of inertia of A2 around AB, denoted as IAB2, using the formula, IAB2 equals to IGX-A2 minus A2 into R2 square. Step 7. Calculate the total moment of inertia of the section around AB, denoted as IABX, by summing IAB1 and IAB2. Step 8. Using the theorem of parallel axes, calculate the total moment of inertia of the section around the centroid, denoted as I, gxx, using the formula, I, gxx equals to I, abx minus a, into r square. In the next slide, we will derive a formula for the entire compound section. Title of this slide now you are watching, is CG calculation of the whole section from base. In this slide, we will calculate the centroid or center of gravity, CG, of the entire compound section from bottom base AB. Calculation for the areas. Area of the trapezium, A1 equals to, A plus B, into H by 2. Area of the rectangle A2 equals to A, into C. Total area, A, equals to A1 plus A2, equals to, A plus B, into H, by 2, plus A, into C. Calculation for the CG of each section from the base. CG of the trapezium, R1, equals to, H into, A plus 2B, by 3 into, A plus B, plus C, equals to H into A plus 2B plus 3C into A, plus B, by 3 into A, plus B. CG of the rectangle, R2, equals to C by 2. Calculation for the moment of each area about the base. Moment of A1 about the base, A1 into R1, equals to, H square into, A plus 2B, plus 3 into C into H into, A plus B, by 6. Moment of A2 about the base, A2 into R2, equals to, A into C square, by 2. Calculation for the total moment of the section about the base. Total moment, A1 into R1 plus A2 into R2, equals to, H square into, A plus 2B, plus 3 into C into H into, A plus B, plus 3A into C square, by 6. Calculation for the CG of the whole section from the base. CG R, equals to, A1 into R1 plus A2 into R2, by A. By substituting the calculated values into the formula, we can determine the exact location of the centroid of the entire compound section. Therefore, R equals to H square into A plus 2B, plus 3 into C into H into, A plus B, plus 3AC square by, 3 into A, plus B into H, plus 2 into A, into C. In the next slide, we are going to calculate the centroidal moment of inertia of the whole section. Title of this slide now you are watching, Calculation of centroidal moment of inertia of the whole section. In this final slide, we will calculate the centroidal moment of inertia of the entire compound section. As we know, the section is composed of two parts, a trapezium, A1, and a rectangle, A2. Step 1. Calculation of the moment of inertia of each section about its own CG. The moment of inertia of the trapezoidal section, about its own CG is given by Igx1 equals to, A, square plus 4AB plus B square, into H cubed by 36 into, A plus B. The moment of inertia of the rectangular section, about its own CG is given by Igx2 equals to, A, into C, cube, by 12. Step 2. Calculation of the moment of inertia of each section about CG of the whole section. The moment of inertia of the trapezoidal section, about the CG of the whole section is given by IGX1 equals to IGX1 plus A1, into R1, minus R, whole square. The moment of inertia of the rectangular section, about the CG of the whole section is given by IGX2 equals IGX2 plus A2, into R2, minus R, whole square. Step 3. Calculation of the final centroidal moment of inertia of the whole section. Since the section is bilaterally symmetrical about the z-axis, the moments of inertia about the x and z-axes are equal. Therefore, the final centroidal moment of inertia of the whole section is given by IGXX equals to IGZZ equals to IGXX1 plus IGXX2. This is the last problem we solved in our Power of Shape Part 2. Now, let's change the shape from a triangle to a circle using the drop-down menu. The only dimension we need for a circle is its diameter. Let's assume a diameter of 5 units. By changing the shape to a circle and inputting the diameter, we find that both I_GXX and I_GZZ are equal to 30.680 units to the power of 4. Formula for calculating I_GXX and I_GZZ is displayed below the results. Now, once again I am changing the shape from a circular to a trapezium using the drop-down menu. The dimension we need for a trapezium are bottom base length, top base length and its height. Let's assume bottom base length is 5 units, top base length is 4 units and its height is 1.5 units. By changing the shape to a trapezium and inputting the dimensions, we find that both I_GXX and I_GZZ are equal to 1.260 units to the power of 4. Formula for calculating I_GXX and I_GZZ is displayed below the results. Now, once again I am changing the shape from a trapezium to a compound trapezium by using the drop-down menu. The dimension we need for a compound trapezium are bottom base length, top base length, depth of the rectangle and the height of the trapezium. Let's assume bottom base length is 5 units, top base length is 4 units, depth of the rectangle is 1.5 units and height of the trapezium is 2.5 units. By changing the shape to a compound trapezium and inputting the dimensions, we find that both I_GXX and I_GZZ are equal to 24.418 units to the power of 4. Formula for calculating I_GXX and I_GZZ is displayed below the result. And there we have it. We've successfully calculated the centroidal moment of inertia for a compound trapezoidal section. This knowledge is fundamental in structural engineering and design, providing a crucial foundation for more complex calculations. I encourage you to practice these steps with different dimensions and shapes to solidify your understanding. Remember, the beauty of engineering lies in its application, so don't hesitate to explore real-world examples. Thank you for joining me on this journey through the world of moments of inertia. I hope this presentation has been informative and engaging. Feel free to reach out if you have any questions or would like to delve deeper into this topic. Until next time, happy learning.